Our next topic of discussion is systems of equations. Now, a system of equations, just as a definition, is when you have multiple equations and multiple variables, usually 2 and 2. So let's say that I had one equation with two variables. For instance, x plus y equals 7. And I asked you to tell me what's the value of x, what's the value of y. Well, you might look at that and say, oh, it could be 4 and 3, or 2 and 5, or 8 and -1. And there are actually an infinite number of possibilities here, right? There are so many possibilities for x and y that it's unlimited. But if I add in another piece of information, so I keep this one, I say x plus y equals 7, and then I add in this other piece of information and say x minus y equals 1, well, could you kind of eyeball this and figure out what x and y are? If you can't, no worries. We're going to talk about a methodical way to do it. But some of you might be able to just look at these equations and say, okay, well, I'm looking for two numbers that add up to 7 but subtract to 1. It's going to be 4 and 3, right? X is 4, y is 3. And again, we will talk about a more methodical way to do that. As we move through this, one concept I just want you to keep in mind is the idea of balance beams. We talked about this when we were solving one equation, right, for one variable. And the idea is in an equation, if I do the same thing to both sides, like a balance beam, everything's okay. What we have here are two balance beams, right? We have a balance beam up here and a balance beam down there. Okay, so let's talk about a methodical way to solve this type of question. There are two ways. So we're going to go over two strategies. The first one is substitution and the second one is elimination. And I do want to stress, both of these methods will always work. Sometimes one works better than the other, and that's why I want to teach you both of them. But if you really, really like one and really, really dislike the other, you can just use that one. All right, so let's start with substitution. Here's the idea with substitution. This x in this equation is the same as this x in the second equation. So what I should be able to do is get x by itself with a little bit of algebraic manipulation and plug it into the second equation. And I'll show you what that looks like. So if I want to get this x by itself, how do I do that? I subtract y from both sides. So x equals 7 minus y in the first equation. Now, this statement, which is a true statement, balance beams, I did the same thing to both sides. This statement I'm going to take and I'm going to plug this value in where I see x in the second equation. And to nip a certain question in the bud that I often get, you don't want to plug it back into itself because that creates what's called an identity and it won't solve the problem. If you have a little extra time, feel free to plug it back into itself, see what happens. But you want to take what you found and plug it into the second equation here. So there's x, right? X is equal to 7 minus y. What we're going to do now in this second equation, wherever we see x, we're going to substitute 7 minus y. So what I get is 7 minus y is equal to 1. Okay. These parentheses are there's no negative in front of here, so these parentheses I can just remove. 7 minus y is the same thing as 7 minus 2y equals 1. Subtract 7 from both sides. I'll subtract 7 from here, and I get negative 2y equals negative 6. Divide both sides by negative 2, and what do I get? I find that y equals 3. Well, how do I find x? Very easy. I plug what I found, that y equals 3, back in to the original equations. Which one? Doesn't matter. Both will work, right? So let's use the top one. X plus 3, right? X plus y equals 7. I'm going to say x plus 3 equals 7. Subtract 3 from both sides. I find that x equals 4. So sure enough, I find that y equals 3 and x equals 4. Now, as I said, there is another way to do this problem, and that way is called elimination. I'm going to draw a fresh set of equations over here, same one. We'll keep this. So exact same problem that we just solved, and if you like that way, you can keep it, but I do want to give you this other one. X plus y equals 7, x minus y equals 1. Remember what I said about balance beams, right? we have two balance beams here. And let me extend the analogy a little bit more. I'll draw the balance beams out. Here's one balance beam, and here's the other balance beam. There we go. There are two balance beams that are level, right? Now, what I have in the first one is basically A equals B, and what I have in the second one is C equals D. These are different expressions. But check this out. Suppose I were to pick A up off of this balance beam and add it over here. And then I picked B, which is equivalent to A, and I add it over here. I have just added equivalent values to two sides of the balance beam, of the second balance beam here. So what I'm saying is I can very easily add or subtract, for that matter, the equivalent values from both sides because these are two balance beams. And let me show you what that looks like in practice. So here's the first side of the first balance beam. Here's the second side, so A, B. And then here's the first side of the second one and the second side of the second one. Well, let me see what's going to help, right? Is it going to be helpful to add or subtract? In this case, it actually you can do either. Just to see this in action, let's add, right? I'm going to add the left sides together. So what happens when I do that? When I add these two together, I find that that's 2x. And when I add these two together, y and negative y, would you look at that? It cancels out. Well, isn't that convenient? And so I find that 2x equals 7 plus 1. I got to add that side, 8. Divide both sides by 2. I find again that x equals 4. Pretty fun, right? I don't know if fun's the right word for that. But we can use elimination, right, by adding or subtracting both sides together. Now, let me make a very important point here. You have to make sure when you're adding or subtracting the sides together that it's going to be convenient. And let me give you an example of what I mean here. So I'll use kind of the same values that we had. So what do we want to say? Let's say 2x plus 3y equals, this is just a different system of equations now, 2x plus 3y equals 17. I want to make sure the numbers add up nice and neatly. And then we have something that says x plus y equals 7. Once again, if I wanted to, I could totally use substitution here. I could get x by itself or y by itself and plug it in. But if I want to use elimination, I can't just add or subtract the equations from each other. I mean, I could, but it would still give me an equation with two variables in it. And my goal with elimination is to eliminate one of the variables. So if I want to use elimination here, I'm going to have to take a step before I do elimination. And that step is multiplying both sides of this equation, the second equation here, so that it will cancel when I add or subtract. Now, if I'm looking at the numbers that I want, I either want to multiply by a 2 or a 3, so that either the x or the y change. So let's do this. Let's multiply both sides of this equation by 2. And I say both sides, I mean both sides, right? So I multiply this, both sides of this second equation, by 2, and I find that it equals 2x plus 2y equals 14. Boom. I multiplied both sides of an equation. That shouldn't change anything. So let me get rid of this original one here because I've manipulated it a little bit. And now I'll ask you, should I add or subtract this? Well, I should subtract because I want these to eliminate. So let me subtract 2x from 2x, 2x from 2x, and 3y minus 2y is 1y, so y is right there, and 17 minus 14, y equals 3. Now that I have the value of y, how do I find the value of x? Well, I just plug it right back into any one of these equations that I had along the way, and when I do that, just in the interest of time, I find that x equals 4, right? One last point to make about systems of equations before we look at some problems. A system of equations is usually expressed with x and y. And from our previous work, we know that x and y are the variables that we use in the coordinate plane. So if I have two equations, again, let me just keep the two that I have here. They're pretty good equations. Let's just keep it and keep using it, right? Let's say that I have x plus y equals 7. I'll draw another line here. X plus y equals 7. And we'll say that I have x minus y equals 1. Well, I hope you recognize that I could easily manipulate this so that it's in the form y equals mx plus b, our good old friend. So y equals 7 minus x. And then down here, if I subtract x and multiply both sides by -1, what do I get? I get that y equals, it took me a second there, x minus 1, right? X minus 1. And if you want to be very exact, you could rewrite this to x minus 7 so that it's mx, or negative x plus 7. Negative x plus 7. So I have two lines here. I have two linear functions. And if I were to graph these linear functions on a graph, which we should be able to do at this point, where do you think they would intersect? Well, they would intersect at the point x is 4 and y is 3. This is where everything kind of comes together. Literally, we're talking about intersection. If I have two lines in the coordinate plane, y equals -7 plus x, right? Or, negative x plus 7, or y equals x minus 1, and I draw those out, I'm going to do a really, really tight sketch over here, right? Negative x means a slope of -1 and a y-intercept of 7, so something like that. Like that. Not a perfectly straight line, but I'm trying. And this is a y-intercept of -1, but a slope of +1, like that. They are going to intersect at the points that we solved for. I should say at the coordinates that we solved for. So let's try some practice here. Let's do some practice with systems questions. Pause the video and give these problems a shot. Which of the following ordered pairs x, y represents the solution to the system of equations below? All right, now I realize that the wording of this question may not be super familiar, but I'm guessing you probably put 2 and 2 together, as it were, right? We're looking for an x and a y, and when we find that x and y, we'll just write it as in this format, x, comma, y. So we're solving for x, we're solving for y, and once we have it, we'll figure out the value of x and y. Okay, so in this case, I would recommend using substitution, the first method that we talked about. And the reason why is because it kind of gives it to us on a platter here. It says that y is equal to 7x minus 45. So why don't we just plug that right in to the other y that we have in the second equation? And I'm going to go ahead and do that right now. So going back through the steps here. I'm going to take this value, y equals 7x minus 45, and I'm going to plug it in there, the whole thing right in for that y. And that's here's what that looks like. X plus 2 times 7x minus 45, boom, equals 30. There it is. So let's distribute and simplify. X plus 14x minus 90 equals 30. I'm going to add 90 to both sides. Add 90 to both sides, like that. I'll combine like terms. This is 1x and 14x. So 15x equals 120. And if I divide both sides by 15, I find that the value of x is 8, right? So x equals 8. Now at this point, right, I could just pick A because there's really only one value for in this list that has x as 8. But I'm going to be a little more thorough here, and just for the sake of practicing, solve for y as well. So y equals, let's just do this, y equals 7 times 8 minus 45. That's 56 minus 45, which is 11. So sure enough, x is 8, y is 11. So this idea of ordered pairs is nothing fancy. It's just a fancy way of saying an x point and a y point, or an x value and a y value. That's it. All right, let's take a look at this one. What's the value of x in this system of equations? All right, so here's a case where we might want to use elimination. You can absolutely use substitution, the way that we did it over here. The downside to that, though, as you may have discovered if you tried to do substitution, is that if you isolate one of these variables, you're going to have a really messy expression that you have to plug into the other one. And I'm not saying you can't do it. I'm just saying it's a lot of busy work. So just looking at this, right, the reason why I lean towards elimination is because unlike over here, where it just gave us what y equaled, it doesn't do that. So instead, I want to eliminate. And as a reminder, that means adding or subtracting so that one of the coefficients goes away. But there's a problem. Do you see the problem? If we add these together, we get 7x minus 6y equals 17. And that's a true statement. There's nothing technically wrong about that. But it doesn't help us because it doesn't get rid of one of the variables. So how are we going to get rid of one of the variables? Well, we have to start with a kind of preliminary step. And that step is multiplying this second equation by 3 on both sides. Now, if you're a little in the weeds at this point, let me just pause and say, I'm allowed to multiply both sides of an equation by anything I want, right? It's a balance beam. If I multiply the left side by 3 and the right side by 3, I haven't changed that equality. If I multiply the left side by Bob and the right side by Bob, same deal. I can multiply both sides of one equation by whatever I want. And here's why that's helpful. I'm gonna carry it over here. So I'm gonna rewrite both equations over here. 2x minus 9y equals 34 on the top. And here, when I distribute it in, I get 15x plus 9y equals, what is that? Negative 17 times 3 is negative 51. Okay. Now, if I add these two equations together, which using the elimination method, I'm totally allowed to do, if I add these two equations together, those cancel out, right? That's helpful because now I have 17x equals, what is that? Negative 17, right? I'm sorry. I added those together. 17x equals negative 17. There we go. It took me just a second. Divided by 17, divided by 17, x equals negative 1. There it is. So the correct answer here is D. Let's try two more. Pause the video and give these a shot. If 3x minus 2y equals negative 2 and 5x plus 3y equals 41, what's the value of 2x plus 5y? All right, so let me write this system out so that I can work with it. 3x minus 2y equals negative 2, and 5x plus 3y equals 41. I could, as always, use substitution here. I totally could do that. I could also use elimination. The problem with substitution is if I try to isolate one of these variables, the expression I get on the other side is going to be pretty nasty, which I'll then have to plug into the other equation, and then it's fractions, and that's not fun. Maybe you ran into that, and maybe you got through it. But in this case, because there are coefficients attached to every one of the variables here, I'm going to use elimination. However, there's another hiccup that I run into. I can't just multiply one of these equations by some number on both sides because to do that, I would have to multiply by a fraction or a decimal. And using fractions and decimals, not a lot of fun. Again, maybe you don't mind it, and maybe you did it, and maybe you got through it, and all that is great. But what I'm going to do here is a kind of a sneaky little strategy. I'm going to multiply the top equation on both sides by 3, right? 3 on both sides. I'm going to multiply the bottom equation on both sides by 2. And here's what that comes out to. On the top, I get 9x minus 6y equals negative 6. And on the bottom, I get 10x plus 6y equals 82. Now, You may ask, like, how can you just do that? How are you just allowed to do that? I'm allowed to multiply both sides of any equation by the same thing. That is allowed, right? It's a balance beam. If I multiply the left side by Bob and the right side by Bob, it's still equivalent. So just kind of justifying what I did there. Well, now look what I can do. I can add these two equations together. We talked about the elimination method previously, right? When I add these two equations together, I get 19x equals 76. Divide both sides by 19, and I find that x equals 4. But I'm not done yet, right? Because I only have the value of x. I need to find the value of y. Well, let's go into here. 3 times 4, I'm just plugging this value that I got for x back into one of the equations, doesn't matter which one. 3 times 4 minus 2y equals negative 2. That's 12 minus 2y equals negative 2. Subtract 12. I get negative 2y equals negative 14, almost there. Y equals 7. But wait, we're still not done because it wants to know the value of 2x plus 5y. So all I got to do now is plug it in. 2 times 4 is 8, plus 5 times 7, 35, plus 8 is 43. All right, now maybe throughout this whole explanation, you were yelling at the computer, yelling at me saying, come on, like there's such an easier way to do this. And there is, and I'm going to show it to you right now if you didn't see it. And if you didn't see it, that's okay. It's good to practice our substitution elimination. Let me rewind to a simpler time, back to where we just had both equations. So rewind the video right now to rewatch that if it didn't make any sense. But I'm going to rewind to the very beginning of our explanation and show you a sneaky little way that we can do this. So we have these two equations here, and we're looking for 2x, the value of 2x plus 5y. I'm going to give you a hint. Let me flip these equations upside down. It doesn't matter which equation I write first, right? 5x plus 3y equals 41, and 3x minus 2y equals negative 2. Are you seeing it yet? Remember that in the elimination method, I'm allowed to just add or subtract two sides of an equation together. Well, if I subtract both sides here, what do I get? I get 5x minus 3x is 2x. 3y minus negative 2y is positive 5y. And 41 minus negative 2 is 41 plus 2, or 43, which is the same answer that we got. So you can always add or subtract equations from each other. That might be a nice shortcut. Okay, let's take a look at this one. In the system of equations above, p is a constant and x and y are variables. For what value of p will the system of equations have no solutions? No solutions? What does that even mean? Well, the way to understand this is to think about a graph, right? And I hope the minute you saw y equals negative 3x plus 2 and y equals p over 6x minus 17, you said, mx plus b, y equals mx plus b, right? Because that's what this is. Now, if I were to graph the first equation in the system, y equals negative 3x plus 2, it probably looks something like this, right? It has a y-intercept of 2, and it has a negative slope, or slope of negative 3. Just a sketch, right? And it's asking me, I want to find the value of p such that these two equations have no solutions. Well, what is a solution in the coordinate plane? A solution is where they intersect. I'm going to repeat that one more time because it's very important. In the xy coordinate plane, the solution to a system of equations is where they intersect. So if I were to say draw, another line like this, I don't know, what P is, but if the other line looked like that, the solution, the XY solution to that system would be at the intersection point. So another way of saying this is, for what value of P will these equations not intersect? They don't have any solutions. And I'm going to rewind here a little bit. Well, if they don't intersect, that means the lines are parallel, right? I want these lines to be parallel. What value of P is going to make it so that these two lines are parallel? Well, and I realize this is a tough problem, but it's one that comes up on the test. If two lines are parallel, they have equal slopes. I'm going to repeat that one more time. I'm repeating a lot here because there's a lot to digest. Parallel lines have equal slopes. So what this is asking me to do at the end of the day is make P over 6 equal to the slope of the first line, which is -3. What value of P is going to make it so that P over 6 is equal to -3? Well, let me just solve for P. Multiply both sides here by 6, and I find that P equals -18.